Swayam Prabha. Digital India. Educated India.
Welcome back, student. In the last class we finished the lecture by introducing a problem that is supposed to be done in the class. So there is a reservoir, it is connected to a pipe is in two different areas, in two different diameters. The total length is 50 meters long, but this is 25 centimeters having a different diameter, and this is having a different diameter. There is a sudden expansion, there is a valve here, there is going to be major losses here, and there is going to be major losses here. Minor losses will be at this particular point here, and there will also be going to be a minor loss at the square entrance. All right. So this is a problem where you will get to understand and practice all the major and minor head losses again. So that is why I thought it to include it as the solved problem. Normally I give this question in the class test or exam for my B.Tech second year students. So I am going to solve this now. It might be a little lengthy problem, but it's important for you to follow what's going on. Okay. So you should try to remember this figure, that a pipe is connected to the reservoir. This is the square entrance, this is the valve, this is the sudden enlargement, and there is an exit. So there is also going to be an exit exit loss, and the water height, the total height is 10 meters in the reservoir. All right. So solution 14. So the pipe system that we have in question, first we should be able to write what all things are there. A, it will have minor losses, right? So what are the minor losses? The first one is square entrance, and the head loss here will be equal to 0.5 V1 square by 2G. We have learned this formula. Since there is a valve, there is a minor loss that is equal to K into V1 square by 2G. K is already given in the question, as I told you, it's 0.2 V1 square by 2G. And the third one is sudden expansion. So HL, so H between 1 and 2, so I call it H12 as V1 minus V2 whole square by 2G. All right, and in the end, then we have next, there exists friction loss HF in pipe 1 and 2, which is given by FL, general formula is FLV square by 2GD, and also there exists an exit velocity. Exit velocity at the end of pipe 2. So this loss of magnitude So entire velocity is lost, so v2 square by 2g. Now we have listed all the type of losses here. Alright, so we have to rewrite the total head loss H as, so starting from here it will be 0.5 v1 square by 2g plus 0.2 v1 square by 2g plus, so in the pipe 1 there will be one major loss as well, FL v1 square by 2g d1, alright, plus in pipe 2 first of all it will be v1 minus sudden expansion v1 minus v2 square by, okay, plus FL2 v2 square by 2g d2, this is the major loss due to the flow, and in the end there is an exit loss v2 square by 2g. Alright, so we have listed down the energy loss. So we start calculating the different so what we can do is we can so we can start writing here the total head is 10 meters, right? Alright, that is, and d1 is, because that is what is going to lose, entire head is going to lose 0.15 meter, and then there is d2 as 0.30 meter, that's we know. So H12, this one sudden expansion is v1 minus v2 whole square by 2g or v2 square by 2g divided by v1 minus 1 whole square. Alright, so we have written, now there are two velocities v1 and v2, and you know what the easiest method to, what is the easiest method to find v1 and v2 is the equation of continuity, and that is what we are going to do next. Alright, so we also know that a1 v1 is equal to a2 v2, right? So a1 d1 square is equal to a2 d2 square. Alright, so using this we can write h12 is equal to v2 square by 2g. Instead of v1, sorry, a1 v1 is equal to a2 v2, sorry, yeah, so this is not correct. So we can transform v1 and v2 in form of d2 and d1. So v2 square by 2g, this will become d2 by d1 whole square minus 1 whole square. So h12 is going to be v2 square by 2g, and d2 by d1 we all know it is 2, right? So 0.3 divided by 0.15 whole square minus 1 whole square. So h12 we can, so this is 2 square is 4, 4 minus 1 3, 3 square 9, so it will be 9 into v2 square by 2g. Alright, so we can simply now write down the value of h as is equal to 10 as v1 by 2g 0.5 plus 0.2 plus 0.02 into 25 by 0.15 plus v2 square by 2g 9 plus 0.02 into 25 by 0.30 plus 1. So 10 is equal to 4.03 v1 square by 2g plus 11.667 into V2 square by 2G. Alright, and we also know that V1 D1 square is equal to V2 D2 square. Alright, so this implies V1 will be V2 into D2 by D1 whole square, implies V1 is equal to 4V2. Alright, so putting this here, we can get 10 is equal to 4.03 into 4 square plus 11.67 into V2 square by 2G, that is 76.14 into V2 square by 2G, and on solution this is going to give V2 as 1.605 meters per second. And if we know V2, we can simply find Q as pi by 4 into 0.30 whole square 1.605, that will give us 0.1135 meter cube per second. Alright, so you see how we have applied the principles of major and minor losses and the equation of continuity to solve such a complex problem like this. Alright, so we go back and we are going to start what we promised is like the Hardy-Cross method. Alright, so what does the Hardy-Cross method say? So if there is a flow like this, there is an inflow and there is an outflow, you see, and there is a loop that is formed. So what we do, we assign the clockwise flows and their associated head losses as positive. So the clockwise flows and their associated head losses are positive. So what we do is at each nodes we distribute Q and write that delta Q is equal to 0. Alright, at each node, and we calculate head loss from Q using HL is equal to KQ square, because you remember head loss was K into V square by 2G, right, or we can simply write KQ square by 2GA square. So basically H can be written as K dash Q square if you bring K by AG. So our head loss is written like this, K into Q square, because head loss is proportional to the discharge square. If the head loss is equal to 0, then that means the solution is correct. If it is not equal to 0, then we apply a correction factor delta Q and we go to the next step. This delta Q is not arbitrary. We have a lead procedure in Hardy-Cross method that will tell what delta Q is, but in principle getting delta HL, sum of all the head losses, exactly 0 is not possible. So we terminate the calculation if we get head loss if it is less than 0.01 meter or delta Q is less than 1 liters per second, we stop the calculation there itself. So instead of 0, we go for a very small quantity. So a reasonable and efficient value of delta Q for rapid convergence is given by this. So this thing you have to remember, delta Q is written as minus of sigma head losses divided by 2 sum of HL by Q. So for each pipe in the loop, we are going to calculate head losses, do the summation of it, not only we are going to calculate HL, but also the value of HL by Q, because if the sigma head loss is not coming 0, we will need that value later. All right. So I'll just repeat the Hardy-Cross method. So at each node you distribute Q such that at each node delta Q should come to 0. It should be an arbitrary Q. Of course, you should satisfy the continuity equation. Suppose 100 is coming from there, and there are two ways you can say 60-40, 70-30 or 80-20, whatever, but it should satisfy the continuity equation. Second thing, you have to do it at all nodes in the loop. So once Q is defined here, Q1, Q2, Q3, Q4 for example, then you start calculating HL. HL is K into Q square. This K either you have to calculate yourself or it will be given also. Both can happen. All right. So you will prepare a table like this. You see pipe, you will say A, B, B, C, C, D. There are 4 pipes here, D, E for example, yeah, could be. It is a circular pipe for example. Then you need to, whatever Q you have distributed, you will write it down here, whatever those are. You have to find HL based on this Q, and thus you also have to calculate HL by Q for each of these pipes, and do the summation here and do the summation here. You have to stop the calculation if this is very near to 0. All right. If not, then we will rely on this value of delta HL by Q by this equation, and you will add this delta Q to each of those Q's in each pipes. Suppose, let's say, if this pipe was 10, if it was 30, it was 20, it was 90, and our delta Q comes to be minus 5 for example, right. Then what you do in the next iteration, so you have to repeat this process again, and in the next iteration the first pipe will have 10 plus of minus 5, this will have 30 plus of minus 5, this will have 20 plus of minus 5, and 90 plus of minus 5. And then you have to make the table again. For each of the pipe you have to write Q, you have to write HL, and you have to write HL by Q. Do the summation here, and you have to stop if this delta HL comes less than 1. So this is the broad explanation of Hardy-Cross method. All right. So I think I will stop here now, and in our final lecture I will start with the solution of this Hardy-Cross problem. So the next lecture is going to be the last one for this module or pipe flows. So thank you so much, and we will start right from this place. Okay. See you in the next lecture.